Again, one of the pleasures of this program is seeing the richness of physics from different subfields brought together. And I think this type of symposium is very unusual at a university for postdocs in one field. And I'll tell you, it's a real treat for me and for everyone here to see the work, leading cutting-edge work done in so many different areas of physics. And we have now the great pleasure of seeing cutting-edge work from another area of neutrino physics by Joshua Spitz.
Can you hear me? Okay, thank you for having me. I'll be telling you about neutrino physics today. The neutrino is one of our fundamental particles. And in particular, I'll tell you about this property that the neutrino has, namely its ability to seem to disappear after traveling a distance. So first of all, thank you to Neil and Jane. It's a great pleasure to be speaking in front of you today. Here's an outline of my talk. I'll first tell you about the neutrino and why we find it interesting. I'll then introduce the idea of neutrino disappearance. And I will tell you how we go about measuring neutrino disappearance. I'll introduce the double show experiment and then tell you about a measurement that we have completed with a number of other collaborations around the world, which is a definitive measurement of the last number or parameter that describes how neutrinos disappear. And then I'll tell you what it all means. So we have our table of elementary particles here. This is analogous to the table of the elements. We have the quarks, the leptons, and the force carriers. Everything that we see around us is composed of atoms. And atoms are composed of neutrons, protons, and electrons. And then the neutrons and protons themselves are composed mostly of up and down quarks. There are also the heavy quarks and leptons. In terms of quarks, we have strange charm, bottom, and top. And the heavy charged leptons, we have the muon and the tau. These particles are mostly only relevant at high energies. They're produced in high energy interactions and then quickly decay into the stable matter particles. There are also the force carriers. These are the particles which mediate interactions. There's the photon, the gluon, and then the W and Z bosons, which mediate the electromagnetic, strong, and weak forces, respectively. And last but not least, we have the neutrinos, which is the topic of this talk. These are neutral, nearly massless particles that sort of famously rarely interact